The electric charges that atoms generate play a large role in the universe. But another force is equally powerful: magnetism. Both electricity and magnetism play a key role in our lives. Early observations of magnetism date back to the 6th century BC, when the Greeks identified rocks containing iron ore as natural magnets with unusual powers of attraction. They came to be known as lodestones because they always pointed toward the lodestar, or lead star, what we know today as the North Star, or Polaris. But why iron ore, or certain other metals, drew or repelled substances remained a mystery. But mariners did learn to take advantage of one of magnetism's key features. Realizing that a magnet aligns itself in a north-south direction, they devised compasses that would point north. Knowingly or not, they were tapping into Earth's magnetic field, which exerts lines of force outward from the poles. Over the centuries, scientists made many discoveries about magnetism, but it wasn't until the 19th century that they began to get a clearer picture of how it works. What scientists now know is that magnetism begins at the same atomic level and with the same particles as electricity. Nobel laureate Leon Lederman explains.
The way the world works is the atom consists of electrical charges. They have names: the electron and the nucleus. That's essentially the two parts of the atom. And the nucleus is tiny little small things sort of floating in the middle of a giant volume in which electrons whiz around. Now, if you have an electric charge that's moving, you create a magnetic field. But if these magnets are misaligned, so that here's a North Pole and a South Pole, and there's a North Pole and a South Pole, and they're all every which way, then the net effect is zero magnetism, and that's what most substances are. They have no magnetism.
Yet the atoms in some substances, such as iron, align their poles in the same direction. The area where this alignment occurs is called a magnetic domain. A substance in which most atoms create magnetic domains will have a magnetic force. One example of this is a bar magnet. The atoms line up in a north-south direction, creating a north pole at one end and a south pole at the other end. As with electric charges, like poles of a bar magnet repel each other.
On your mark, get set, go!
While opposing poles attract each other. Earth is a magnet with magnetic north and south poles. Emanating from each is an unseen series of magnetic field lines in the surrounding space. Scientists believe that this field is caused by liquid iron in the planet's outer core. Heat-driven convection currents drive the motion of the molten iron, which generates a continuously changing geomagnetic field. This magnetic field also protects Earth from a stream of charged particles emitted from the sun. Without this barrier, life on Earth would likely be far different because of the destructive impact of the sun's radiation. Yet there are weaknesses in the poles that allow radiation in. Occasionally, it results in the colorful light shows called aurora borealis and aurora australis that appear in the northern and southern night skies. There is a unique relationship between magnetism and electricity. When an electric current flows through a wire, a magnetic field is produced. The result is electromagnetism. The magnetic field produced is similar to fields found around a bar magnet. Run an electric current along a wire that's placed near a magnet, and the wire rotates. That continuous rotation is what's behind the electric motor. Like this one, that for the last 70 years has run Coney Island's electric Astroland Cyclone roller coaster. There may be no better or more thrilling example of how electrical energy becomes mechanical energy. Electromagnetism doesn't stop there. Reverse the process by moving a magnet near a coil of wire, and you'll generate electric current in the wire. This is the basis of an electric generator, which has powered our way of life for more than a century. The current produced by a generator may be either direct or alternating current. Direct current is a charge that moves in only one direction. Batteries produce a direct current. The electrons, which are present throughout the circuit, move around the circuit, beginning at the negative end of the battery and ending up at the positive end. Alternating current, like that produced at the Hoover Dam, results from an electric charge that changes direction periodically. It's supplied to our homes because it permits the changing of voltage as needed through the use of a transformer. Without a transformer, electric power would be distributed at lower voltages, but at higher current. Higher current would lead to increased transmission loss in the power lines and greater expense. Therefore, electricity from Hoover Dam is stepped up to 230,000 volts for long-distance travel, and then stepped down for use. Magnetism does more than supply power to our homes. By means of electromagnetic waves, we send data instantly around the world. When you think about it, our world has been and continues to be transformed by electromagnetism. Perhaps even the Greeks sensed this when they found themselves attracted to the lodestone so many centuries ago.